commenting on soap bubbles? So basically, first of all, soap and water are used to create soap films and soap bubbles, and you need to do this. You'll learn about it a little bit later, but you need to do this because soap actually decreases the surface tension of water, which allows bubbles to form instead of them just popping. So soap and water, when left alone, will become what's called a minimal surface, which is basically a soap film, which is just flat. The curvature will be 0. And so this is a soap film. So a soap bubble is a film of soap and water that is encompassing a given volume of air. The bubble creates the smallest possible surface area with that given amount of air possible. So it's as a bubble moves, it's always changing shape until it reaches something like a sphere. It has the least possible surface area. But other shapes can also, and for example, if you have 2 little wands, you can this is called a catenoid, which is proven to have the smallest surface area for something of that size. So you can do other things. So these are just various different soap bubbles. These, as you can see, when 2 of them connect, they actually share a wall and to conserve surface area. And one will actually bulge into a bigger one if they're different sizes. And of course, as more get on, you get really cool shapes. And if you have 3 or more, they actually 3 at a time will form on one wall and have 120 degree angles, all to save space so they can only use one surface area. And all of these laws are all known as Plateau's laws. This is very impressive. So what's important here is the stuff in this like reddish pink. Basically, the air pressure, the film of the soap bubble will always be balanced by the air pressure inside the bubble and the air pressure outside of the bubble, which is smaller than the air pressure inside. So to balance that out, the air pressure on the outside, which is atmospheric air pressure, needs help from the surface tension of the bubble, which is why you need soap, so that the surface tension actually pushes in with the atmospheric pressure, so that your bubble, once you've blown it, doesn't get bigger or smaller. It just stays the same size. And this is the equation. The difference between the two, the inside pressure and the outside pressure, is T, which is surface tension divided by R, which is the radius of the bubble. And so the curvature of a bubble depends on its shape. But a typical spherical bubble will have a constant mean curvature. And basically, mean curvature is how you calculate the curvature of a point. Basically, you take the curvature of one line and the curvature of a perpendicular line, and when they meet, you find the average of the two. Curvature is measured in force. No, it's not force. It's measured in, it's like a fancy, it's like Gaussian or something. It's a fancy thing, but basically you take the curvature of the two and you average them. So basically, a soap bubble should always be a perfect sphere, and a soap film should always be on, it's like on a wand that you saw at the very beginning, should be flat. This isn't always true because you can blow in different ways, and gravity will affect bubbles. So often bubbles are different positions, but a basic bubble will always be a perfect sphere. And that's what a soap bubble actually wants to be, because that has the minimum surface area possible.
Alright, so again, as Anand said, when 2 bubbles meet, this is only for 2 bubbles, they form a perfectly flat surface to minimize the surface area, and the angle between the flat surface and the plane formed by a line that is tangent to the sphere of the bubble meet at 120 degree angles. And the 3-dimensional geometry behind soap bubbles is really intriguing. So if you have 4 bubbles, you can insert another bubble in between all 4 of them, and this will form a tetrahedral. Well, they will form a tetrahedral, which is like a pyramid shape or triangular pyramid. And the more bubbles you increase on the outside, the more sides the 3-dimensional object on the middle will have. So if you have, for example, 6 bubbles on the outside, it will form a cube on the inside. But on the shape on the inside, it doesn't have flat surfaces. It's actually the the bigger spheres, and this is all reiterated in this from BBC.
Is there
Look
sound?
at the speakers.
If they touch each other, they could save material for both of them by sharing a common wall. And so they do. If they can save surface area by taking advantage of their environment, they will.
So when you've got just one bubble, the sphere is the most efficient shape. But as we add more bubbles, we see the geometry changing. So in this case, we've got 4 bubbles, and you can see them meeting at a point. But put a shape in the middle, we don't get a spherical bubble. We get, in fact, a little tetrahedron. 4 faces, they're not exactly flat, they're parts of spheres. But each time, the bubbles are trying to find the most efficient shape for the arrangement of bubbles. So now we've got 6 bubbles, we've got a little cube appearing in the middle. This is nature's laws at work. The universe is always trying to find the most efficient solution it can. And as we pop them, the bubbles change, finding the most efficient, until we're left with a sphere again.
There's no choice.
But what's most remarkable is that those solutions are so often neat geometric shapes. Wow, that's a dodecahedron, that's fantastic. And they're almost perfect pentagons, aren't they? That's really surprising. They're not bulging really very much at all. So 12 bubbles around make 12 faces, and the most economical shape that they can make, the lowest energy, is the dodecahedron.
Yep.
That's just unbelievable.
And that guy was
That's so cool. Also, if you were wondering, like when it fell and hit the bottom, and the bubble
2 minutes.
burst. When the bubble burst in that video, bubbles have this unique thing where obviously they're really easy to pop if you just touch them because they're so thin because of the surface area. That they're really easy to pop. Another way they pop is soap bubbles actually soak in water, and the mixture in a bubble surface actually is soap on top of water. If they get too big and the soap gets too stretched, the water will evaporate into the air and then it pops. But you can also just touch it before.
That's it?
yes.
All right. Can somebody turn the lights on for us? Questions? So you can. Yes.
How big could you theoretically make it?
As long as you have, I mean, on Earth it depends on materials and gravity. Gravity is a big factor because at a certain point, it's, you know, unless you've got way up like on a huge building, you can only make such a big bubble that it wouldn't be touching the ground. But if you had like an endless amount of soap, huge materials, and lots of people, lots of space, you could make a potentially massive bubble. Probably wonderful. Yeah.
If you're making bubbles and you can use the same amount of soap, but then when you blow them, you can sort of choose how much air to put inside the soap. If there's less volume encased, does that mean it's a stronger bubble because of the surface area?
What the bubble will always do is, it could do a couple things, but what the bubble does is that it just gets as small as possible. The surface area doesn't, or, you know, the surface tension doesn't get stronger. It's just the bubble shrink, it contracts to the given area.
You said when 3 or more bubbles meet, they always meet at a 120-degree angle.
When
Is
you
that
have-
true for 3 or more, or is it just
When you
for
have
3?
3 or more bubbles, like let's say you have 12, like in that one,
Right.
they will touch in groups of 3. They will be like meet at these like walls in groups of 3 with 120-degree angles for each bubble at the wall. And there will be multiple groups of 3 if there are more bubbles.
So that's why they always meet at a 120-degree angle?
Yeah.
Wow. I didn't know that.
So they might be different sizes, but they will meet with the same. They always have the same angle because they have the same surface tension.
I have a whole bunch of questions, but I'm I'm gonna wait till
If you'd
tomorrow.
like, if you'd like to.
I mean, they're questions that you can't answer, because we're just gonna have to explore it tomorrow and see what we can do. Any other questions?
So theoretically, you could make an infinitely number of shape and an infinite amount of sides. Or you could just keep going with the amount of sides by just adding bubbles to that, like with the things, the bubble within the bubbles.
I think theoretically it might be possible, but in real life, like like the film, like at the beach, like when the water rushes in and you see all those, that film of all these little bubbles, that's different soap bubbles touching together. But obviously, and there's thousands, but obviously, whether it's gravity or just time evaporation with the water evaporating, they will disappear. Theoretically, I guess you could have an infinite number. But I don't think it's possible.
The difference is theoretical and
Yeah.
real.
Yeah.
Any other questions?
People do it really quickly.
Okay, that was really good, guys. It was really good. Thank you. I want to mention just a few things about